Okay, so we have a transverse wave travels from left to right. So we are moving in that direction. The diagram below shows how a particular instant of time, at a particular instant in time, the displacement of particles in the medium varies with position. Which arrow represents the direction of the velocity of the particular marked P? So this is a specific instant of time. If we think of the next instant of time, this wave would have moved from left to right, like we've said. So this wave is moving over in this direction. So I could draw its next position in time, something like that. And so you can see that that point P would have actually moved down to there. So the velocity would be obviously in that direction. So C is your correct answer for that one. Question 14. We have the graph shows how the displacement varies with time for an object undergoing simple harmonic motion. So it's displacement versus time. Which graph shows how the object's acceleration A varies with time? Now, we do have these formulas over here. This would actually be the formula that would be relating it, except it would be x is equal to x0 sine omega t with a negative sign there, because it's a negative sign graph. What we haven't got here, we could actually just work through here. We actually find that it's going to be d, because when we find the velocity, it's going to become it's minus x0 omega cos omega t, and acceleration, when I do the next differential, becomes x omega squared sine of omega t. So we have that one over there. But we could also use, probably the easiest way to do this is just to use our definition for simple harmonic motion, which is minus omega squared x. So your acceleration is always in the opposite direction. So when we look at these three graphs here, when we look at them, when we look at this over here, this is going in minus. So I'm looking at a graph that is doing the same thing, but it's proportional, you see. So as the one increases, the other increases, but it's always in the negative. So it would be this one over here. That is the only proportional to the negative graph that we have. This is in the same direction. This is actually in inverse proportion situation. So it's got to be D. This corresponds to that sort of relationship between the two. If you need further help with that, please come and talk to me about that. Here we have light travels from air into glass as shown below. What is the refractive index of glass? Now, the refractive index of air we can take to equal 1. And we are looking for the refractive index of glass. Now, obviously we're going to be using Snell's law here, where n1 over n2 is equal to the sine of theta 2 over the sine of theta 1. Now, what is important is that we always work with the angle to the normal, which is the line that's 90 degrees to the surface where the ray of light is coming in. So we've got that as coming in there. So we're definitely going to be working with Q and S. So it could be D, and have we got another Q and R here? We don't have another Q and S here. We don't have another Q and S. So it's got to basically be this one over here. There's no other one, because we wouldn't be working with any of the others. But let's just put it into our formula just to make sure. If we take this as n1, so it would be n1, which would be 1 over the n glass, is equal to the theta 2 is this one over here, which is going to be the sine of of S, the sine of S over the sine of theta 2, which is Q, and then we've got to do the inverse of it. We've got to switch both sides over, so it's going to be NG is equal to the sine of Q over the sine of S, and so it's that one over there, it's D. For question 16, it's basically a knowledge question. Which of the following electromagnetic waves has a frequency greater than that of visible light? Now, remember we have the formula here that C is equal to frequency times wavelength. Now, in a specific medium, your C is constant. So, as your frequency increases, your wavelength must decrease, and vice versa. So, if you've got a frequency that is greater than visible light, it means that its wavelength must be less than for visible light. The wavelength would be lower. Now, we know that radio waves and microwaves are all long wave radiation. I think you should all be quite clear on that. Infrared rays are actually also long rays. You'll see this also in the climate change energy unit. Infrared is the light given off, or the wavelength given off for heat. When something is warm, it gives off energy in the form of infrared, and it's slightly longer. So it's the ultraviolet is the one that's the higher frequency. These are the ones that cause damage to skin and so forth, and the ozone layer protects us from the ultraviolet radiation.